Okay, so now we're going to continue our review for the Unit 4 exam, and now we want to go to lesson number 22 on magnetism, and I hope that you can see me. Okay, with all of this stuff up here, I hope that you can still see me, and we've still got a little bit of room down here where we can finish out our topics. So this is going to be out of chapter 24 of your textbook. And we want to talk about the cause of magnetism is the electric current. So as a charged particle moves, if it's a single particle, that charged particle will have a velocity v. If it is a wire, it's going to have a current I, but both of them cause magnetism. So anytime an electrical charge, whether it's positive or negative, is moving, it creates a magnetic field. Okay, what about conservation of magnetic charge? So that means that you cannot take a magnet and break it in half and isolate the North Pole and the South Pole, because what you get is two new magnets when you do that. So it's impossible to isolate magnetic monopoles. So that's what conservation of magnetic charge means. And then be able to draw the magnetic field B. All right, so now we've got another letter here. So this is the magnetic field B, and its official metric unit is the Tesla. So draw the magnetic field of a straight wire using the right-hand rule, so that the thumb points in the direction of the current and the fingers curl around the wire. Now remember, the current has to be positive. We always do things in terms of positive charges. So if you had a positive current in the wire, then it curls around it like this. But if you use negative charges, what do you think? Negative charges would flow in the opposite direction, so then it would curl like this. And then be able to draw the magnetic field of a magnet. So if you have a north pole and a south pole of a magnet, can you draw it? Okay, can you figure out the direction of the magnetic field? So could you put arrows on it? So you're going to use a teeny tiny north pole, and if you put a north pole right here, it would be repelled. So that would mean that it's going to come out of the top, and then it goes in the bottom. And then it goes out the top, and then it goes in the bottom. So that would be the magnetic field of this. If we take it and we rotate it, then the arrows would be going into the south, and they would be coming out of the north down here at the bottom. And then can you draw the magnetic field of the Earth? Well, it's the same picture. So the magnetic field of the Earth is as if there is a bar magnet inside the Earth, which there is not, but it's as if there's a bar magnet inside the Earth. Okay, then you had the inductor. So the capacitor stores the electric field. The inductor, which is a coil of wire, stores the magnetic field. And it also stores magnetic energy. So both a capacitor and an inductor can store energy in the form of electricity. In the capacitor, it stores it in the form of electric charges. And in the case of the inductor, it actually stores electrical current in the coils of the wire, and then that's what's making the magnetic field on there. Okay, let's take a break, and when we come back, we will talk about magnetic force.